Right. So, very good afternoon to you all. I welcome you all for today's EMF session. I'm just waiting for the students to join quickly, but only 40 students so far joined. Anyhow, I will start my session. I hope my voice is audible to you. After um, 3 days or 4 days gap, I'm taking the class. Let me recollect what are the topics I have discussed so far. Yes. So I have been discussing EM wave propagation in different media. Yes, that is unit 5. My first part is the EM wave propagation in different media. What are those different mediums that we have considered? 4 mediums: free space, lossless dielectric, lossy dielectric, and good conductor. Free space, lossless, lossy, and good conductor. These are the 4 different medias we have considered. And I have defined how different medias are characterized in terms of conductivity, permittivity, permeability. Free space, sigma is equal to 0, epsilon is equal to epsilon naught, mu is equal to mu naught. Lossless, lossy dielectric, good conductor. Right? This is how the characteristics of the media are defined. And EM wave propagation in free space, the Maxwell's equations are modified. So these are the 4 Maxwell's equations which are modified according to. So Maxwell's equations are modified according to medium characteristics, right? According to medium characteristics. So here sigma is equal to 0, epsilon is equal to epsilon naught, mu is equal to mu naught. So these are the medium characteristics, and Maxwell's equations are modified accordingly. In all types of medias, I have been discussed wave equation, propagation constant, phase constant, attenuation constant, velocity, and intrinsic impedance. So these are the 5 or 6 parameters which I have discussed in all type of media. So the procedure is very simple. So taking equation 1, applying curl on both sides, and simplifying, we'll get the wave equation. And wave equation is compared with the basic wave equation. So this is the basic wave equation, right? And equation 6 is called the wave equation in terms of electric field. We can also express wave equation in terms of magnetic field by considering equation 2 and follow the same process, applying curl on both sides, simplifying, and we'll get wave equation in terms of magnetic field. So this is the general form of wave equation. So these two are compared, right? So these two equations are compared. So comparing these two equations, we'll get 1 by v square is equal to mu naught epsilon naught, and we'll get velocity of the wave. With what velocity wave propagates in free space? With what velocity wave propagates? With a velocity which is equal to velocity of light, right? And here the Maxwell's equation is converted into its phasor form, right? Converted into its phasor form. So in phasor form, this is the wave equation: del square es is equal to gamma square es and where gamma square is propagation constant, which is expressed as alpha plus j beta. Propagation constant is a complex number which can be expressed as alpha plus j beta, and where alpha is attenuation constant and beta is phase constant. So comparing these two equations, we will get gamma square, right? We will get gamma square, and gamma is equal to imaginary part, right? It has only imaginary part, right? So therefore real part is 0, right? And imaginary part beta, phase constant, is equal to omega root mu naught epsilon naught. So beta is equal to omega by v naught, since v naught is equal to this, and intrinsic impedance eta naught is equal to e by h. So this relation I have derived later. I have derived this relation, e by h relation. Later I have derived this expression, and eta naught is equal to 377 ohms or 125. And also I have given the relationship between wavelength and the phase constant, lambda and beta, right? So this is about the wave propagation in free space. So once wave propagation in free space is clear, wave propagation in the remaining medias also same, because we will follow the same procedure to all, right? So coming to the next topic, lossy dielectric media, right? So lossy dielectric media is characterized like this: sigma not equal to 0. So therefore Maxwell's equations 1, 2, 3 and 4 are rewritten like this. And procedure is same: taking equation 1, applying curl on both sides, and simplifying, we will get wave equation like this. So this is the wave equation in terms of electric field, right? And gamma square is propagation constant, right? So comparing these two, right? Comparing these two, we will get gamma square is equal to minus omega square mu epsilon plus j sigma omega mu, and so on like this. So alpha square minus beta square, equation 7, and alpha square plus beta square, equation 8, right? So I'm not going deep into the explanation, because already I have explained all these steps, right? So therefore on surface level I'm moving fast. So alpha square plus beta, so we have alpha square minus beta square, and this is alpha square minus beta square, and this is alpha square plus beta square. So solving these two for alpha and beta, we will get equation 9 and equation 10. So here alpha not equal to 0, right? So whenever sigma not equal to 0, we will get alpha not equal to 0, right? So whenever sigma not equal to 0, you will get alpha not equal to 0. So sigma not equal to 0 for what? Lossy dielectric media and conducting media, right? Lossy dielectric media, conducting media, sigma not equal to 0. So therefore for both lossy dielectric media and conducting media, alpha not equal to 0. So alpha not equal to 0 in the sense what? Attenuation exists, right? The waves amplitude will get attenuates as it propagates in the media. The waves amplitude will get attenuates. That means loss, right? Loss in amplitude. So this is how we can define wave propagation in lossy dielectric media. And coming to next topic. So next topic here, without doing much derivations, I have taken alpha and beta expressions directly, right? So because for a good conductor, I have the condition. Man, so what is the condition I have? sigma is very much greater than omega epsilon, or sigma by omega epsilon is very much greater than 1. So this is the condition I have, and alpha and beta are the function of sigma by omega epsilon here, and here we have sigma by omega epsilon. So therefore, applying this condition, right? Applying this condition in both alpha and beta, in both the expressions of alpha and beta, and simplifying, you will get alpha is equal to beta, right? Alpha is equal to beta and not equal to 0. So alpha is equal to beta is equal to root over pi f mu sigma, right? Pi f mu sigma. And here I have summarized free space, lossless dielectric media, lossy dielectric media, and good conductor. 4 medias I have summarized with alpha and beta, right? And intrinsic impedance. So this is the common equation derivation for all 4 medias, intrinsic impedance. So taking this equation, this is one of the Maxwell's equation. So taking this equation and expanding, right? So expanding like this. So expanding this equation like this, right? And equating ax term, right? Equating ax term on both sides, and we'll get equation 2. And um, writing magnetic field component hy and hz in phasor form, right? Hy and hz in phasor form, writing those two expressions in phasor form like this, right? Hy is equal to hy naught e power minus gamma z, and hz is equal to hz naught e power minus gamma z, right? So as I said earlier, z is the direction of wave. I'm assuming that the wave is propagating in z direction, right? Even more clearly, e power minus gamma z, in the sense the wave is propagating in z direction. Wave is propagating in positive z direction, right? In positive z direction. E power gamma z, right? E power gamma z, in the sense the wave is propagating in negative z direction, right? Here e power minus gamma z and e power plus gamma z. So the symbol, the sign minus, in the sense minus z, right? Minus z, in the sense the wave is propagating in positive z direction, and plus z in the sense the wave is propagating in negative z direction, right? So therefore I'm assuming that the wave is propagating in positive z direction. So that is the reason why here the sign negative here, minus sign here, e power minus gamma z, minus sign, right? And substituting this equation in equation 2 and differentiating, right? Differentiating with respect to y and with respect to z, right? And simplifying, you will get intrinsic impedance, this one. So this is the final expression for intrinsic impedance. Eta is equal to square root of j omega mu by sigma plus j omega epsilon, right? So for free space, as we know that sigma is equal to 0, eta is equal to 377 ohms. And for lossless media, eta is equal to root over mu or mu naught by epsilon or epsilon naught. So this is equal to 120 pi root over mu or epsilon naught. right? So this is eta for lossless media, right? Eta for lossless media, right? So we can determine intrinsic impedance only when if we know mu r and epsilon r of the media, right? So without knowing mu r and epsilon r values, we cannot determine intrinsic impedance. And similarly, third one, for a lossy dielectric media, lossy dielectric and a good conductor, right? Lossy dielectric media and a good conductor where sigma not equal to 0, where sigma not equal to 0, intrinsic impedance is equal to j omega mu by sigma plus j omega epsilon. That's it, right? So this equation we will take directly, and depending upon sigma value, right? Depending upon sigma value, we will determine intrinsic impedance, right? That's it. So this is about intrinsic impedance. And skin depth, right? So skin depth, or it is also called as depth of penetration, right? So that means when wave incidents on a conducting media, right? When wave incidents on the conducting media, it penetrates to some extent, not deep into the conducting media, because EM wave cannot travel into a conducting media, right? It cannot travel into a conducting media because for a good conductor, sigma is equal to infinite. Conductivity is infinite. So when conductivity is infinite, then the attenuation constant is very high. So therefore, the entire wave will get lost, right? So EM wave will get lost inside a conductor, not on the surface, but inside a conductor, right? It's because um, the wave's amplitude will become 0, right, inside a conductor. So now skin depth, when wave penetrates through a conducting media um, to the depth of 1 by E times, right? To the depth of 1 by E times E naught, or to the depth of delta, right? To the depth of delta, then wave's amplitude will become 1 by E times E naught, right? Wave's amplitude will become 1 by E times E naught, and that is called as skin depth. That means the wave's amplitude will become 37%, right? Wave's amplitude will become 37%, right? And that is called as skin depth. And skin depth is equal to 1 by attenuation constant, right? 1 by attenuation constant, right? So here e power minus gamma z, and this is all the derivation, right? How we can derive this one, that is the derivation part, right? So therefore, for a good conductor, here we have defined that um, uh, delta is equal to 1 by alpha, and for a good conductor, alpha is equal to beta is equal to root over pi f mu sigma, right? Pi of mu sigma, right? So previously we have defined that. So this one, right? So pi of mu sigma, alpha is equal to beta is equal to pi of mu sigma, this equation, right? So taking that equation directly and substituting here this one, right? So for a good conductor, as we know that sigma is equal to infinite, right? For a good conductor, conductivity is infinite. So therefore, if conductivity is infinite, alpha is equal to infinite, right? When alpha is equal to infinite, what is skin depth? Skin depth is 1 by alpha, and which is equal to 0, right? So for a good conductor, conductivity is infinite, therefore conductivity is directly proportional to what alpha, or alpha is directly proportional to sigma, right? So if conductivity is infinite, attenuation constant also infinite. If attenuation constant is infinite, then skin depth is right, skin depth is zero. So skin depth is zero in the sense what? Skin depth is zero in the sense, skin depth is zero. Skin depth is zero in the sense the wave does not penetrate into the conducting media, right? The wave the wave does not penetrate into the conducting media. The wave lies on the surface of the conducting media, right? The wave lies on the surface of the conducting media, and the wave inside a conductor does not exist. That is very important point, right? So that is about skin depth. And then we have done a related problem. H is given. We have determined epsilon r, omega, and E from the given data, right? So that is what we have discussed in our last class, right? And now let us move on to another new topic, polarization, right? So polarization is another small topic, and definitely you will get a short answer from this, right? So definition, all definitions. So definitions they will give for short answer questions, right? So here the polarization definition I will give first. Definition. So polarization means polarization means here the polarization is defined in terms of electric field component, right? So as we know that magnetic field in the sense what, which contains electric field and magnetic field, right? And this is the direction of wave propagation, right? K is the direction of in other words ak bar, right? Ak bar is the direction of wave propagation, right? So electric field and magnetic field and the direction of wave propagation are mutually perpendicular, right? Are mutually perpendicular. Let us say ae bar is the direction of electric field, ah bar is the direction of magnetic field, and ak bar is the direction of wave propagation. Direction of electric field, and this one is the direction of magnetic field, and this one is the direction of wave propagation, right? So direction of electric field, direction of magnetic field, and direction of wave propagation are mutually perpendicular, right? They are mutually perpendicular, right? So they are mutually perpendicular, right? So that means what? AE bar cross AH bar is equal to AK bar, right? AE bar cross AH bar is equal to AK bar, right? For example, let us say the electric field is in X direction, magnetic field is in Y direction. Then what is the direction of wave propagation? AX bar cross AY bar is AZ bar, right? Is AZ bar. So therefore here X, Y and Z are mutually perpendicular, right? So therefore the polarization is defined in terms of electric field component, right? In terms of electric field component. That means when wave is propagating, when wave is propagating in a media, when wave is propagating in a media, how electric field is changing, how electric field is oriented with respect to time, and that is defined as polarization, right? So polarization is nothing but orientation of electric field in space with respect to time, how electric field is changing with time, right? How electric field is changing with time in space is called as polarization, right? So therefore behavior of behavior of electric field, electric field component at some fixed point in space, right, is called as um, polarization, right? Or orientation, orientation of electric field strength, right? Orientation of electric field strength in space with respect to time, right? In space with respect to time is called as polarization, right? So depending on the orientation of electric field, polarization is categorized into three types, right? So one is linear polarization, linear polarization, and second one circular polarization, and third one elliptical polarization, right? So these are three classifications in polarization, right? So first one, linear polarization, linear polarization, right? So name itself gives you how electric field is oriented. So in case of linear polarization, the electric field varies linearly, right? The electric field varies linearly with time, right? Linearly with time. That means a straight line. The orientation of electric field is a straight line. So for example, in space, so as I'm defining polarization with respect to electric field. So let us say this is the X component of electric field, and this is the Y component of electric field. And what is the resultant electric field? The resultant electric field is this one, right? This is the resultant electric field, and this is the angle theta, and where theta is equal to tan inverse Ey by Ex, right? Magnitude of Ey and magnitude of Ex, right? So this is theta, and theta is constant at all times. Theta is constant at all times. Let us say this is at t is equal to t1, right? And at t is equal to t2, that is some other time, right? At some other time. So this is the electric field Ex and Ey, right? So at t is equal to t2, at t is equal to t1, this is the locus point. So this is the locus point of resultant electric field, and t is equal to t2, this is the locus point of electric field at different times. So therefore theta remains same, right? Theta is constant. So therefore the variation of electric field is linear, right? It is a straight line. If you join all the focus points, right? If you join all the focus points of electric field, you will get a straight line. So that is called as linear polarization, right? Linear polarization. Um, the electric field has both Ex and Ey components which are in phase, which are in phase, which are in phase, and the resultant electric field, makes an angle theta, makes an angle theta which is constant, which is constant with time, which is constant with time, is called linear polarization, right? Is called linear polarization, right? And linear polarization again is of two types. Linear polarization is again two types. One is linear vertical polarization and linear horizontal polarization, right? Linear vertical polarization and linear horizontal polarization. So linear vertical polarization in the sense what? If the electric field is vertical to the plane of incidence or to the plane of polarization is called as a linear vertical polarization, right? If electric field, is vertical to the plane of polarization, to the plane of polarization is called linear vertical polarization. If electric field is horizontal, right? If electric field is horizontal, then it is called as linear horizontal polarization. For example, let us say this is the boundary, right? So this is the boundary, and this is the vertical axis, right? And let us say the wave is propagating in z direction, right? And this is the incident wave. As we know that when wave incidents on the boundary, it reflects, part of the wave reflects. So this is a reflected wave, and part of the wave transmits, right? part of the wave transmits, and this is called transmitted wave, and this one is incident wave, right? So instant wave is EM wave, and which consists of electric field, and this is the electric field, incident electric field, and magnetic field, right? Magnetic field, HI, right? So here the magnetic field is indicated with dot, right? Dot. If the magnetic field indicated with cross and a circle, cross and circle, then it is called as this is called as magnetic field outside, the direction of magnetic field outside, and this is called as H inside, inside to the screen, right? So therefore magnetic field outside, coming outside from the screen, right? And cross in the sense magnetic field going inside the screen, right? So you just imagine. So therefore electric field and magnetic field are mutually perpendicular, and the direction of wave propagation is also mutually perpendicular. So this is the direction of wave propagation, AK bar, right? Wave is propagating in this direction, right? In this direction. So therefore electric field, magnetic field outside, and this is AK bar, they are mutually perpendicular. In this case electric field and the plane, right? See here, you just see it, this is the plane, right? So this is the plane background here, so this is the plane. So this plane, so this plane is called the plane of polarization, right? The plane of polarization, this plane, this one, right? The plane of polarization, and the electric field is parallel, right? The electric field is parallel to this plane. So this is the plane, and this is the electric field, right? So electric field is parallel. If electric field is like this, right? If electric field is like this, it is perpendicular. If electric field is like this, it is parallel. Like this, like this, like this, or any direction, it is parallel, right? So parallel to my hand. When let me show you. Yes, right. And if the electric field is like this, we can say that it is perpendicular to my hand. Let us say my hand is a plane of polarization, right? So therefore depending on the electric field, whether it is parallel to the plane of polarization or perpendicular to the plane of polarization, we have two types, right? And next one, the second one is um, circular polarization. Circular polarization, right? So circular polarization, as we know that electric field has Ex and Ey components, right? Electric field has Ex and Ey component. The amplitude of the amplitude of Ex and Ey is equal and out of phase by 90 degrees, right? Out of phase by 90 degrees. Such wave is called as circularly polarized, right? Such wave is called circularly polarized. Let me explain in detail, right? So here, let us say the electric field. So this is Ex and this is Ey bar. the resultant electric field is ER bar. So this is the resultant electric field at T is equal to T1. At T is equal to T2, we have this one. So this is EX bar and this is EY bar. Then the resultant electric field is this one, right? So this is the resultant electric field at T is equal to T2, right? So similarly, at T is equal to T3, we have, so this is EY and this one is EX and the resultant electric field. So this is the resultant electric field. So this is T is equal to T3, right? So similarly, at T is equal to T4, at T is equal to T4, again we have, so this is EX and this one is EY, then the resultant electric field. So this is the resultant electric field ER. So this is at T is equal to T4, right? So here, if you can observe, right, if you can observe from T1 to T2, so what is the phase shift here? So this is 45 and let us say this is 45 and the locus, what is the locus point of resultant electric field? So this is the locus point of resultant electric field at T is equal to T1 and this is the locus point of electric field, resultant electric field at T is equal to T2 and this is the resultant electric field at T is equal to T3 and at T is equal to T4, this is the locus point, right? So from T1 to T2, the phase difference, so this is 45 and this one is 45, right? Why 45? Because EX is equal to EY, right? In the definition I have given, EX is equal to EY, equal, amplitudes are equal. So therefore, here 45 and here 45. So therefore, the phase difference is 90 degrees. And similarly, from T is equal to T2 to T is equal to T3, again this is 45 and here is 45, total 90 degrees. And here it is 45 degrees, so total 90 degrees. Therefore, the resultant electric field is at every time it is moving with 90 degrees phase shift. So therefore, if you join all the locus points, T is equal to T1, T is equal to T2 and T is equal to T3, T is equal to T4, if you join all the locus points, you will get a circle, right? You will get a circle, right? A circle, and hence the wave is said to be circularly polarized, right? The wave is said to be circularly polarized, right? Example, and let us say Ex is equal to Ex naught is the amplitude. In other words, let us say 2 cos omega t minus beta z, and Ey bar is equal to, right? Ey bar is equal to Ex bar, in the sense the wave is propagating in x direction, and Ey bar is equal to 2 cos omega t minus beta z plus 90 degrees Ay bar. Let us say this is equation 1 and this is equation 2, right? If you compare equation 1 and equation 2, we can say that the electric field, right? Electric field. So resultant electric field is equal to Ex plus Ey bar. right? Ex plus Ey bar is the resultant electric field, and we can say that here the amplitudes, right? Amplitudes are equal. So what is the amplitude here? 2, and here what is the amplitude? 2, right? Amplitudes are equal. Ex amplitude of Ex and Ey is equal, and the phase difference here 90 between these two is 90 degrees, right? So they are out of phase by 90 degrees, right? Then the electric field is circularly polarized, right? Electric field is circularly polarized. Now elliptically polarized. Third one, elliptically polarized. So elliptically polarized in the sense what? The electric field orientation is an ellipse, right? Electric field orientation is an ellipse. For example, this is the electric field orientation. Electric field is in elliptical shape, right? So this is circular, and this is an ellipse. When electric field is moving elliptically, then it is called as elliptically polarized, right? So when we will get an ellipse, when Ex, magnitude of Ex is not equal to magnitude of Ey, and they are out of phase by 90 degrees, right? They are out of phase by 90 degrees. Then the wave is said to be elliptically polarized. That is only the difference between circular polarization and elliptical polarization. In circular polarization, Ex is equal to Ey, right? In circular polarization, Ex, amplitude of Ex is equal to amplitude of Ey. But whereas in elliptical polarization, amplitude of Ex and Ey are different, right? Are different. Then it is said to be elliptically polarized. That is only the difference between circular polarization and elliptical polarization. So for example, if Ex bar is equal to 2 cos omega t minus beta z Ax bar, and Ey bar is equal to 3 cos omega t minus beta z plus 90 Ay bar, then we can say that the wave is said to be elliptically polarized, right? So why elliptically polarized? Here the amplitude, it is 2, and here the amplitude is 3. So therefore amplitude of Ex is not equal to amplitude of Ey, and they are out of phase by 90 degrees, right? They are out of phase by 90 degrees. Then the wave is said to be elliptically polarized, right? So this is about polarization, right? So polarization is the orientation of electric field in space with respect to time. In other words, how electric field is uh, or is moving in space, how electric field is changing with respect to time, right? And that is polarization. And depending on how the electric field is moving, polarization is classified into three types: linear polarization, circular polarization, and elliptical polarization. Linear polarization in the sense when electric field is a straight line, right? Then that means the variation of electric field is straight line, it is linear. And the circular in the sense the variation of electric field is a circle, then it is circularly polarized. And elliptically polarization in the sense when the wave is elliptically moved in space with time, and it is called as elliptically polarized, right? So this is about polarization, right? uh, so let us close the discussion here. Just a minute.